Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to look at the difference between an observational study and an experiment. And we're going to talk about why we might use each one of those. So in statistics, we have some sort of curiosity or question to begin with. And then we go out and collect data to help us answer that question. Sometimes our questions are easily answered by collecting that data. For instance, we have some simple question like how many drownings occur at the beach in Sunnyvale, USA each month. So then to collect the data, maybe we just go to the local records and see how many drownings occurred on the beach each month. Collect our data, answer the question. Or maybe we want to know how much ice cream is sold on the beach in Sunnyvale, USA each month. So again, we just go maybe to each one of the ice cream stands there and ask them, how much did you sell this month? Or maybe we look at the tax records to find out how much ice cream was sold there on the beach that month. We just collect our data to help us answer the question. When we do that, we're just simply collecting data that already exists. We're just observing that data, measuring or counting that data. Then that is an observational study. No type of manipulation or interference is occurring. I'm just simply observing data. So an observational study is just one where researchers simply collect the data by observing, by watching, maybe by measuring something or counting, but they're not interfering and they're not manipulating any sort of groups. So in both of those cases, we did an observational study to collect that data. But maybe I have something a little more complex in mind that I need some more information. So maybe as I collect my data to answer these two questions, I realize that as the number of drownings rise in Sunnyvale, USA, the number of the sales of ice cream goes up too. Like as more ice cream sold, there's more drownings occurring. So I start thinking, well, maybe those two are related somehow. Maybe selling ice cream on the beach is bad. Maybe we shouldn't be selling ice cream on the beach. Maybe by selling ice cream on the beach, we're causing people to drown, and we don't want that to happen. So sometimes we want to determine a cause and an effect type of situation. We want to collect data to see, does selling more ice cream on the beach cause drowning to go up? Is there some sort of relationship there? So again, maybe we go out and we collect the data on both of those variables, just like what we talked about. We looked at tax records, we look at the drownings, and we see. We've collected our data, we see they both go up, but is it really the sales of ice cream that's causing those drownings? You know, maybe I'm so excited by my findings, I even go to my local city council and I say, look, we got to stop selling ice cream on the beach because the more ice cream we sell, the more drownings occur. We don't want drownings, so let's stop selling ice cream so there'll stop being drownings. But maybe it isn't the ice cream that's causing those drownings. Maybe there's some other variable out there that's lurking or confounding my study, messing it up a little bit. But maybe my thinking isn't all clear. Maybe those two variables, the sales of ice cream and the number of drownings, correlate. They go together, but maybe sales of ice cream doesn't actually cause drownings. Can you think of another variable that might make both of them go up and both of them go down at the same time? Something like the temperature outside. Maybe when it's cold outside, people don't buy ice cream and they don't go swimming so they don't drown. But as it gets warmer, people start buying ice cream, they swim more, and so therefore there will be more drownings. And so the higher the temperature, both of them go together. So maybe it's not the sales of ice cream that's causing the drownings. Maybe there's some other variable out there, like temperature, that's causing the two to happen together. So I was just doing an observational study. I was just collecting data that already exists. But then I'm like, wait, maybe it's the ice cream causing the drownings. Or maybe some other researcher said, hey, I think sales of ice cream causes drownings. And I'm like, that's a little weird. I don't think that's true. So I want to do something a little more advanced to help make sure that one is causing the other. So in order to do that, I might do an experiment. An experiment helps me to eliminate other variables. So for instance, maybe what I do is I make sure that the temperature at two different pools is exactly the same. And I make sure that I have two sets of kids that are identical, or adults, or whatever type of people I have that are exactly the same. Same race, same weight, same age, same income level. Everything about them is exactly the same. The temperature of the water is exactly the same. I have everything in the pool exactly the same. Then I have ice cream for both of them. That's exactly the same. And in one group, I give them the ice cream, and then I have them go swim. And in the other one, I don't give them ice cream, and I have them go swim. And I do this over and over and over again. And then I count to see, does this group that have ice cream, are there more drownings on that side than there are on that side? If yes, there are more drownings when everything else is the same, then I can start to go, well, maybe it is the ice cream that's causing it. But if the number of drownings are the same in both groups, regardless, they still have the same number of groups, even though drownings, even though I'm giving this group ice cream and I'm not giving that group ice cream, then maybe it's not the ice cream that's causing it. So an experiment helps me to eliminate all of those other outside variables, like weather, to help me determine if one is causing the other. By the way, ice cream doesn't cause drownings. It would be the weather or the temperature that makes both of them rise together. An experiment is an investigation in which a hypothesis is scientifically tested. So in other words, we have some idea, ice cream causes drownings, and we want to test it. So we do it in a scientific method. We do things like make everything the same except for one change. In an experiment, researchers assign subjects to treatments. So in other words, I assigned one group to have ice cream and the other group didn't get ice cream. So the subjects got a treatment. They got ice cream. To see what effect the treatments have on a specific variable of interest. So we're only looking at that one variable. Does ice cream cause drownings? And we make everything else the same. So an experiment helps us to be able to look better at cause and effect. So in statistics, we would love to be able to do experiments on all of our studies to help us to find that cause and effect. But sometimes we don't need it. For instance, when I just had nice, simple questions, I could just collect my data to answer it. But anytime I'm looking for that cause and effect, I'm going to want, if I can, to do an experiment. So that's kind of the introduction to what the difference is between an observational study, where we simply observe data that already exists, and an experiment where we eliminate all outside variables that we can and then try to look at just one specific variable. In statistics, we'll collect data based on some question that we want answered. And sometimes when we collect that data, we realize that two variables have some sort of relationship. Maybe as one of them increases, as measurements increase, the measurements of another one also increase. Or maybe as the measurement of one decreases, the measurement of another decreases. Or maybe as one increases, the other decreases. Or maybe as this one decreases, that one increases. We call that relationship correlation. And when we do that, we have two different types of variables. We have the explanatory variable and the response variable. And the explanatory variable is just a variable that explains or maybe predicts what the other variables' measurements will be. So that explanatory variable, if this one increases, it might let me know, it might predict, it might explain that my response variable, my other variable, is also going to increase. I can then predict. So the explanatory variable is just the one that explains or predicts, and the response variable is the one that I'm actually testing. Let's look at some examples. A researcher collects various data on children and their reading habits and scores. The researcher finds that the kids that have books in the home score better on reading tests. In this case, my explanatory variable is the number of books in the home. And the response variable is the score on the reading test. So this researcher has found that as the number of books in the home increases, the score on their reading test increases. So the explanatory variable is number of books, and the response variable is the score on the reading test. Here's another example. A researcher follows firemen from a fire department and collects data. The researcher finds that when more firefighters are present at a fire, more damage occurs. So here, the researcher collects the number of firemen at a fire and realizes that that will help predict or explain the amount of damage that occurs at the fire. So the more firefighters that are there, the more damage occurs. So those two are correlated. And your explanatory is the number of firemen, and the response variable is the amount of damage. A researcher finds that short 8-week classes have higher grade averages and higher pass rates for students. So in this case, the researcher looked at how long the courses were, and then the GPA, or the grade that was made in the course. So the explanatory variable was how long is the course, and the response variable is that grade that was made. So the explanatory variable just predicts or explains our response variable. A lurking or confounding variable might interfere or influence a statistical study. So first, what is a lurking or confounding variable? Well, a lurking variable is a variable that is not among the explanatory or response variables, and yet it may influence the interpretation of relationships among those variables. And a confounding variable is a variable whose effects on the response variable cannot be separated from another possible explanatory variable. Let me explain. So a lot of times when we collect data on two variables, we might notice some sort of relationship between those two variables, where we see one variable and we think it might explain why the data of another variable. But it might turn out that there's some outside variable, some variable that we're not taking into account, that actually might help to explain the relationship between those two variables. That might explain what's causing or what's influencing those two variables. Let's look at some examples. Here, a researcher collects various data on children and their reading habits and scores. The researcher finds that kids that have books in the home score better on reading tests. Should the researcher assume that just giving kids books will make them better readers? Should we go to the school board and say, hey, let's just give $100 worth of books to all the schools and to all the kids in our district? Is that going to make all our students better readers? What might make the number of books in the home help also increase the reading level of our students? So some outside variables that might influence those reading scores might include things like financial ability. Maybe the parents who can afford books in the home can also afford something like a tutor to help their students when they're struggling with something like reading, so that it's not the books in their home that's causing them to be better readers, but that financial security is what's actually helping them be better readers. Or maybe another outside variable that might be lurking out there might be the interest in books. Parents whose priority is buying books for their home might prioritize reading with their kids at night. Or maybe it's the kids themselves. Maybe they really enjoy reading, and so they get their parents to buy them books as presents. And so maybe it has nothing to do with having the books themselves, but because they're interested in reading, they have more books in the home, and they have their reading level is better. When you're good at something, sometimes you like to do those things. So it might not just be the books themselves that's causing the higher reading level. It might be something like financial security, or the prioritization of reading, or the interest in reading. Those are lurking variables that are outside, that are influencing our study. Here's another example. A researcher follows firemen from a fire department and collects data. The researcher finds that when more firefighters are present at a fire, more damage occurs. Should we send fewer firefighters? So here we collected data on the number of firemen, and we collected the data on the damage that occurred. And someone saw that the more firemen we send, the more damage that occurs. So should we send less firemen? What's an outside variable that might influence those two things? What might cause us to send more firemen and also for more damage to occur? Maybe it's the size of the fire that actually causes that. When you have a large fire, you send more firemen. And of course, a large fire then would make the damages occur. So that's that outside variable that we're not actually collecting data on. Here's another example. A researcher finds that short 8-week classes have higher grade averages and higher pass rates. Should a college offer only 8-week classes? So again, we're looking, and we go out and we look at the fact that these 8-week classes collect data on the length of the class, and then we collect data on the grade average. And we see that in an 8-week class, those summer or 8-week classes like mini-mesters, the students tend to do better. So the researcher goes to the college and says, hey, let's just make all our classes 8 weeks. That's obviously helping our students do better. But maybe there's some outside variables that are actually influence those. Can you think of some other outside influences or variables that might make students choose an 8-week course and therefore their grades be better? Like, for instance, in the summer, we offer 8-week courses. What type of student might take those 8-week courses? Maybe they're at a university and they're coming back to a community college like Temple College, in order to take those summer classes. Well, students that can be at a university might have a better academic skills. Maybe students who choose to take those 8-week classes have better academic skills to begin with. Or maybe those students who choose to take 8-week classes are more motivated, and so they're more motivated to do better in the class and therefore make better grades. So that motivation level or that academic level, both of those would be outside variables that would influence and help them choose a short course, and would also help them choose to do better in the class. It might help them to raise their grade point. So just making everybody take an 8-week class might not be advisable, because if they don't have that characteristics, maybe their grades wouldn't be as well. So those lurking and confounding variables are just outside variables that might influence our study. Let's look at how we can control for lurking or confounding variables when we design our statistical study. So one way we can do that is we can identify or specify our population. When we get ready to begin studying and we're going to collect our data, we need to make sure that we are actually identifying the population that we want to look at. And we may sometimes need to narrow that population down. Maybe we're not looking at all of America, or all adults in America, or even all adults within the ages of 20 to 30 in America. Maybe we narrow that down to adults in Texas between the ages of 20 and 30. We just need to identify and make sure that we're being careful with what is our population. Are we looking at all trees? Or are we looking at pecan trees? Are we looking at pecan trees in a certain area, Texas? Are we looking at a certain height of pecan trees, a certain age of pecan trees? So just identifying and specifying our population when we begin is really, really important. Then when we collect our data, when we collect our sample, we need to make sure that our sample is representative of that population. So in other words, if we collect data from Temple College students, but our population was the United States, Temple College students don't represent the whole United States. We would need to get a sample from lots of different places around the United States if our population was the United States. Now, if our population is just students at Temple College, then maybe collecting data from some of those students would be a representative sample. So we have to make sure that we are getting a representative sample. What is it that our population looks like, and make sure that all the parts of our population are represented. Then we need to consider outside variables. What are some confounding or lurking variables that might be out there? And then help to account for them when we're designing our study. For instance, we looked at ice cream sales and drownings. Well, we need to make sure that we eliminate that weather. So when we're designing our study, our weather across the board should all be the same. Or maybe when we looked at kids and reading levels, that the financial ability of all the students should all be the same. So things like to take into account that when we get our population, our sample, when we collect our sample, we're trying to collect a sample that is similar all the way across. So if we have a certain number of in our population, we want it to be representative, and then we want to account for any differences to make sure that we're eliminating those outside variables to begin with. Then we need to recognize that while observational studies, we can start to account for those and help to make them better, really experiments are the best. They are a way that we can control our environment. In an observational study, a lot of times we cannot control those outside variables. So experiments are just better for controlling it. Now, we can't always do an experiment, but when we can, that's the way we should go. Then when we design our experiment, if we are designing an experiment, there are certain things that we can do as well to help control for those confounding and lurking variables. One thing we can do is we can randomize our control group and our treatment group. Our control group is just that group that we're not giving a treatment to. We're just looking at them and seeing what happens without the treatment. And then our treatment group is the group we are actually giving a treatment to. We should randomize that. I shouldn't be choosing, all the tall people on one group and all the short people in another. It should be completely randomized. We should use a placebo when appropriate. So think about medical testing when you're looking at a new drug. Just the fact that I'm getting a drug, even if it's not or I'm not getting a drug, might influence the outcome of the study. It turns out that just receiving something sometimes would make me better. So we want to use a placebo when appropriate. And a placebo is just a fake treatment. It's a treatment that looks like the real treatment, but isn't actually a treatment at all. And that just eliminates me from thinking I'm getting a treatment, and therefore that thinking making me better. So we want to use a placebo when we can. We want to use a single blind or double blind method in an experiment when possible. So a single blind experiment is when I, as the researcher, know who's getting treatment and who isn't, but the subjects who are getting the treatment don't know. But sometimes, without even realizing it, I may bring some sort of confounding or lurking variable in just with my knowledge of who's getting the treatment or not. I might not realize it, but I may walk over to the people who are getting the treatment and say, hey, how are you doing today? That treatment's going all right? Whereas when I go to the patients that aren't getting the treatment, I may say something like, hey, how's it going today? That treatment going all right? My words may have been the same, but my body language may be different. And that may bring in some confounding and lurking variable. So a single blind is when I know as the researcher, but they don't know. But a double blind is even better. And a double blind, I don't know and they don't know who's getting the treatment and who doesn't. And that way I can't bring any sort of confounding or lurking variables in with me. So double blind experiment is when both the researcher and the subjects don't know. Single blind is when the researcher knows, but the subjects don't know. You want to be able to replicate the experiment, and you should replicate the experiment and see if you get the same results. When we do that, then we know that we're helping to control for those lurking variables. And then last but not least, you need someone to review your design and study and your actual collection of data and such. That peer review lets you know that you've just, that way your peers can give back feedback and say, oh wait, did you think about this outside variable? And so that helps to control for those variables. So when you're looking at studies, statistical studies, and someone's saying, hey, I think this causes that, or this variable explains that, you can look at the design of the study and start to decide, did the design help to control for outside things? You yourself can start thinking about, is there some outside variable that's causing a relationship between both of those variables? So designing our study is important for helping to control those outside lurking or confounding variables. In statistics, we ask some question, and then we go out and we collect data to help us to answer that question. And there are two different ways that we can do that. We can simply observe data that already exists by using an observational study, or we can take and do a little manipulation and give a group a treatment in order to collect our data. So let me give you some examples. In our first question, we have, does the color of a basketball influence the number of times a shooter sinks a basket? So maybe me, as the researcher, thinks that if I give all my team members a blue basketball, they'll sink more baskets than a team that has all orange basketballs. So I want to do some experiment, or I want to do some study to help me to see if that's true. One way to do it is to simply observe. I could just place blue and orange basketballs out on the basketball court and ask my players to go choose a color basketball. Then write down the color they've chosen. Then let them go and from a specific spot, shoot basket after basket after basket and count the number of baskets that they've made. That would be an observational study. I'm simply observing. They chose their own ball. I didn't provide the ball for them. They chose their own ball and then they just shot baskets, and I wrote down what color ball they chose and how many baskets they made. If I wanted to be a little more precise though, so for instance, in this observational study, there could be outside or lurking variables that are there that I've not realized. So maybe everyone who chooses a blue basketball happens to have some vision impairment and it makes it more difficult for them to shoot a basket. Or maybe people who choose the blue basketball are older and it makes it harder for them to choose a basket. All the people who choose a blue basketball on their own may have some sort of similar characteristic, and that's the reason that they chose the blue basketball over the orange basketball. And that similar characteristic may be what's really making them shoot the basket better or worse. So to help eliminate those outside variables, those lurking or confounding variables, we like to perform experiments. Experiments are just a little more rigorous. They help to eliminate those lurking variables. So here's an example of how I can answer that same question using an experiment. Here, instead of allowing them to choose their own basketball, I'm going to divide my subject in, or actually I'm going to give the same subject 2 balls. First, I'm going to give him an orange ball, and I'm going to have him stand in a certain spot and shoot baskets and count how many he does correctly, or she. Then give him the blue basketball and do the same thing, so that I know it's the exact same shooter that's shooting. There's not any differences there. They don't have any separate characteristics. So I could do that for multiple players to collect data, and that way I'm keeping everything the same shooter, the same type of shot, the same environment that they're shooting in, and I can help to eliminate those outside variables. So here, this is an example of an experiment where I've given them the treatment of a blue ball, and that control group then would be the orange ball, as opposed to the observational study where I just let them go choose and I just record. Here's another question we could answer 2 different ways. Does smoking during pregnancy affect birth weight? If I'm doing an observational study, I'm simply observing. So I might ask several pregnant women, did you smoke during pregnancy? And I'll just record what their answer is. That's data that already exists. And then when the baby is born, I weigh the newborn baby. And again, I can write down that data that already exists. So in this, I'm just simply observing what's happening. But maybe it turns out that maybe the birth weight of the babies is smaller, and in which case, maybe it's not the smoking that's causing it. Maybe it is people who choose to smoke have some characteristic that is the same. Maybe all the women who choose to smoke have less education, and so they don't know to do prenatal care. And that prenatal care or the lack of prenatal care is really what's causing the low birth weight and not the smoking. Or maybe people who smoke have some other characteristic. They're hard workers, and that hard work is what's causing the low birth weight and not the smoking. So there are outside variables that could be affecting my study. So to help eliminate those outside variables, it would be best to perform an experiment. An experiment is just more rigorous. It eliminates those outside variables. So instead of just asking the pregnant women, do you smoke, and weighing the baby, for an experiment, what you'd have to do is take the women and divide them into two groups. You would want your women to be exactly the same in every way that you can think of: education level, financial level, the number of people in their home, what they're eating during pregnancy, how much they're working during pregnancy, how much they're sleeping. You make your two groups as much as possible the same. Their race, their age, all that exactly the same. And then one group you would say, you're not going to smoke during pregnancy. And the other group you would say, you're going to smoke during pregnancy. You would give them that treatment of smoking. Then when the baby was born, you would weigh the baby to see how much they weighed. And by eliminating all those outside variables, you would then know, oh, I'm pretty sure that the smoking is what is influencing the baby's weight. But you can maybe see a problem with that. Ethically, if I think that you smoking during pregnancy is going to make your birth weight of the baby be less, that wouldn't be ethical. So in this case, I can't actually perform an experiment on this. So instead, I have to do an observational study. So sometimes we can do observational studies. Sometimes we can do experiments. We would prefer to be able to do experiments, but experiments take time, they take money, and they take the ability to be able to do it. So sometimes it's just not possible. There's a little bit about observational studies versus experiments. Let's look at when and why we use observational studies versus experiments. So when we have two variables that we're trying to look for the relationship between those two variables, and we would like to exclude all other variables so that we're just looking at the relationship between those two variables, the best way to go about that is to do an experiment. Experiments are the most rigorous way to find that relationship between two variables. It helps us to eliminate all other outside variables because we can set up our environment and we can choose our subjects so that everyone looks the same. Our environment is all the same, and that helps to exclude our outside variables. Then we can better tell if there's a relationship between two variables. And with experiments, we can also replicate them because we've set it up in such a way where we have our groups and we're giving those groups a treatment, and then we can look at the outcome. Since we've set our study up, our experiment up in a certain way, then we can replicate that and do it over and over again to see if we get similar results. Experiments are the best way to study that relationship between two variables, but sometimes that's almost impossible to do, or it's really, really hard. For instance, if it is ethically not possible for us to do an experiment, for instance, if I'm trying to find the relationship between smoking and birth weight, I don't want to tell a bunch of women, you must smoke during pregnancy. That's just not ethically okay to do. So sometimes we have to use an observational study. In addition to that, there are reasons to just use an observational study. If I'm not looking at multiple variables, I'm just looking at one variable that I want to collect data on, then using an observational study and just collecting data on something that already exists makes sense. So observational studies have a tendency to be easier. They require fewer resources than experiments. They're not as hard to set up. Although some of them still have difficulty, it's not as difficult as doing an experiment. And sometimes it's just the only way that you can collect data is by simply observing. Sometimes it's just not possible to divide into groups and give a treatment to one group. Sometimes you just have to observe data that's already there. So that's kind of an explanation on when we use experiments and why versus observational studies. Math Made Simple is some math. Thanks for watching. In statistics, there are many different ways to perform studies. So when we have a question that we want answered and we gather data, there are lots of different ways to go about that, depending on the question we're asking. Let's look at a couple of different ways to do those studies. First, let's look at a cross-sectional study versus a longitudinal study. A cross-sectional study is just a study that happens on a snapshot in time. It's when we go out as researchers and collect data at a specific defined time, and we get a snapshot in time of our data. So, for instance, a Washington Post ABC News poll taken in September of 2009 showed 66% of Americans had been hurt financially by the recession. We get a snapshot in time of September 2009 of what's happening financially to Americans. Here's another example. Researchers determined the number of glaciers on the mainland of Greenland in October of 2018. Again, we're only gathering data here in October. We're getting a snapshot of what the glaciers look like there in October 2018. Many of our political polls are this type of cross-sectional study, where we're just getting a snapshot of what's happening at that moment in time. We can compare that to a longitudinal study. A longitudinal study happens over a long period of time. It's when researchers are looking over a long period of time and collecting data over that period of time to see if they can find some sort of pattern or some sort of links to behaviors over that time. So for instance, researchers wanted to determine the effects that social behaviors in teens have on health in adulthood. A group of 15,000 students was chosen and followed with periodic interviews over the course of 14 years. So they watched them from their teenage years into adulthood to see what behaviors they had when they were teenagers that affected their health when they were adults. And you can see over that 14 years, it was a long amount of time to follow them. Here's another example. Researchers collect data on the number and size of glaciers on the mainland of Greenland from 1900 to 2000. So now we're looking at those glaciers over a long period of time. We've collected our cross-sectional data all along for a long period of time. So now it's a longitudinal study, and we can look at patterns that have happened to those glaciers over time. So the difference between cross-sectional is it's just a snapshot in time, whereas longitudinal happens over a long period of time. Let's look at a couple of different types of studies, the meta-analysis and the case study. A meta-analysis is just a study of studies. So I have several different researchers that have collected data on some topic, and I come along and I use the data from all of those different studies. I am now conducting a meta-analysis. So a meta-analysis is just that. It's a statistical analysis that combines the results of multiple scientific studies. A meta-analysis can help identify patterns across many studies on the same topic. So here's a couple of examples. Oceanographers study research on the effects of tsunamis in several locations in the world. So, this researcher is looking at tsunamis in Japan, and this one's looking at tsunamis in another location, and this one's looking at tsunamis in another location. And I come along and I look at all of their data to try to find some patterns amongst all of those tsunamis. I'm now doing a meta-analysis because I'm doing research based on the research of others, of multiple studies. Here's another example. Researchers look at research from various studies on glaciers around the world to determine the change in glacier size. So again, they're looking at the research from other studies to help them determine those changes and see patterns on glaciers. Right now, we're having the coronavirus research that's occurring all over the world. So there are all kinds of different studies going on what kinds of medication maybe would help the patients. And there are people that look at all those different studies to help them see patterns. And when they're looking at lots of different studies, they're doing a meta-analysis. A case study, however, is a study about a single person, group, or a situation where we look at multiple variables in that one case. So for instance, researchers might study the shooter from the Pulse nightclub shooting to determine what led to the shooting. So we're going to look at that shooter and we're going to look at everything in their life, their education level, what was their home life like, when did they, what were their interests, how did they spend their free time, what kind of job did they do. We're going to look at all of the variables to see what we can determine about that particular person. That's a case study where I'm studying that one person. Here's another example. Researchers study a specific pack of timber wolves to determine changes in behavior, environment, and breeding habits. So they look at the timber wolves and they look to see in all the different things involved. What are they eating? Where do they migrate to? How many pups are they having? They look at all the different variables that they're involved to help them learn more about that specific pack. And that's a case study. So a meta-analysis is just a study of studies, whereas a case study studies one specific thing and looks at lots of different variables. Math made simple is Simpson Math. Thanks for watching.